Hello, everyone. I think we will start in a minute, so let's get settled. Hey, good afternoon, everyone. And on behalf of Texas Industrial Energy Efficiency Program, welcome to today's Water Forum on energy efficiency and decarbonization in the industrial use of water. We are glad that you can join us, and also hello to our participants on Zoom. And just a reminder that this event is being recorded. For those of you who are not familiar with TIEEP, its mission is to provide thought leadership, sharing ideas, technologies, opportunities, and timely information to Texas industries on ever-improving energy intensity, reduced environmental impact, resilience, and enhanced social and economical development. TIEEP's industry focus is the oil refining and the chemical sectors. It is organized by UH Energy at the University of Houston, and it is funded by a grant from the State Energy Conservation Office. So water, energy, and carbon emissions are inextricably linked, and the opportunities abound to improve energy efficiency while saving water and decarbonizing. And in today's hybrid event, industry experts and the suppliers present cutting-edge tools, strategies, and examples for attaining these integrated objectives, both in existing manufacturing facilities and in new plants with emerging technologies. Today's presentations will address these three subjects on streamlining the search for energy savings in utilities, designing pump systems to reduce energy consumption towards greater sustainability, and in the energy transition, reverse osmosis and economics of green hydrogen production. And you can find more about the details of these presentation and the abstracts and the speaker bios on our event page or by scanning the QR code on the screen. For those who are joining us on Zoom today, we will be placing a link in the chat options and you can access more details there. So before we begin with the technical program, I have a couple of important announcements. The first one is that today's Water Forum is being co-hosted by the South Texas section of American Institute of Chemical Engineers. And their monthly meeting will follow after our program at 6:30 p.m. And we would also like to acknowledge STS AICHE's gold sponsor, XPS Cooling Technologies. I'm sure you are familiar with their Marley brand of cooling towers. And we are joined today with Chris Kapp, JP Wallace, Kurt Hoyer, and Anthony Size from SPX Cooling Technologies. And can Chris and others please raise their hands? And yes, so feel free to reach out to them during the networking event or after the Water Forum, and they will be more than happy to provide you more information on these technologies. Second announcement, the PDH certificates will be available at the end of the Water Forum for professional engineers who need them. And they can be used for continuing education credits in Texas and also in other states. However, regulations can vary from state to state, so feel free to check the regulations on the other states as well. All right, with that, let's start our technical program. And please join me in inviting our first speaker, Mr. Clayton Harris. He is the engineering manager at Hydrus Works LLC, and he will be presenting on streamlining the search for energy savings in utilities. So please give a hand for Clayton Harris.
Uh, Hello, my name is Clayton Harris. I'm the engineering manager for Hydrus, and like I was introduced, I'm gonna talk about streamlining the search for energy savings in utilities today. A little bit of background and context, or I'll cover a little bit of background and context on who we are and why we focus on utilities. I've got a better approach to utilities that I want to talk about. That's kind of the meat of the presentation. I've got some examples towards the end that I'll share with you, and then we'll close it out and leave a little bit of room for discussion. So what we do at Hydrus is we help sites to struggle with their industrial utilities. Most of our clients are refiners, and so whether you're looking at improving your utility system, planning for the future, whatever it is you're trying to focus on utilities, we should be able to help you with that. So I'm going to preach to the choir a little bit. If you've ever spent any time in utilities, we think utility systems are important. They serve the needs of multiple processes, and they are the only systems that can impact an entire operation. So it's not hard to imagine if you lost a steam system, you lost your air system, how quickly the processes are going to shut down. So they are important systems, and the demands on these systems can vary broadly from day to day and sometimes season to season, but these demands are rarely going down. These utility systems are put under more stress and more strain over time as time goes on, as more expansions, as more needs are put on these systems. They're tough systems. They are giant and old. They span the entire site, and they've been around since the beginning. So since that first column went up, there was probably a utility system built nearby to support that process. And so they end up being these complicated Frankenstein monsters that have been kept alive over the expansions of the plant over 50, 60, 70 years. And because of this, knowledge tends to be fragmented. You're lucky if you've got a single person that knows a whole lot about a single utility system, let alone a team that knows everything about all the utility systems. The breadth is just too large. These systems are just large, complicated spaghetti bowls that are difficult to manage and difficult to control. So, historically, they're low on the totem pole. They are not the most attractive systems to work on when it comes from a dollar standpoint. Improvements in utility systems don't always have a clear ROI. And if they do, they're typically measured in decades instead of months or years. And so most of the time when we get involved in a utility project, it's because there's a recurring pain point or a process improvement that knows it's gonna be using a lot more air, steam, water, or whatever it is they're after. And because of this, utilities tend to be full of opportunities to reduce energy consumption and reduce water consumption. Often there's opportunities to optimize operations in general, improve your reliability, fault tolerance, and then also sometimes you can get some process improvements out of it. So we think utilities do better with what's called a continuous improvement approach or continuous improvement cycle. And if you're not familiar with this, it's a little bit different than the project container that a refiner, a petrochemical site might do. But I got in here 3 basic steps here, and I'll talk a little bit more about this towards the end. But the first step is to standardize the work. That's to kind of lay out your documentation and rules for when you're going to tackle a utility system or when you're going to deal with a problem in a utility system. The second is to make incremental improvements, and I want to stress incremental because utility system is, again, this giant spaghetti bowl with a bunch of components, and so you've got to improve these little components one at a time. You can't make one blanket improvement to a utility system and solve all your problems with it. And the third step is to retain and fortify that knowledge. So you're going to learn something about it when you make an improvement to your utility system, so you've got to hold on to that knowledge. You've got to fortify that knowledge and make sure that it doesn't leave when the next person comes to tackle a problem with the utility system. Once you've done step 3, it's time to go back to step 2. So it's a cycle. So you want to make an improvement, learn from your mistakes, learn from your knowledge, make an improvement, and continue and repeat over and over. So where to start? The best place is at the beginning, of course. And I'll define, how we think about a utility system. But all a utility system is in this context, in a refiner's context in particular, is the infrastructure and equipment that provides the essential resources to support the processes. So that's water, steam, air, hydrogen, nitrogen, fuel gas, all the fluids that are in a big piping network that's going to be delivered to the main process so that it can do whatever it is that it needs to do. Consists of suppliers and consumers. Usually there's a handful of suppliers that are meeting the needs of a wide variety of consumers. Consumers can vary in type and size and location. Again, they're going to be scattered all over the site. Oop, there we go. Stand right there. So you're going to need a tool. Again, there can be hundreds of components influencing utility systems. So These individual components are often well understood because they were designed by somebody with some intent for a process. So they understood their little box that their project was in. They knew how big their pump needed to be. They knew how big the turbine that drove that pump needs to be. But how all these components act together is not always as well understood. And so you're going to need an analysis tool to help you with that. This is a big system, so you've got to be able to understand how it behaves as a whole. And the right tool needs to be able to answer any question you can throw at it pretty quickly. Accurately, it's got to help you understand your operational demands, conditions, capacities, your degraded conditions, your shortfalls, help you conduct a gap analysis, help you plan for your future needs, understand what kind of conditions are going to put your system at risk and the processes they serve at risk. And so a model is going to be the right tool for that. And in this case, in a utility system, not just any model, but a hydraulic model. So all of these components, in most cases, are going to be connected by a large pipe network. And so that means they're all hydraulically connected, which means that any component can actually influence any of the other components on the system. So it's not hard to imagine if you turn a pump on one side of the site, you're going to see an impact on the other side of the site. Or if you turn a large user on one side of the light, it might affect all the other users on the site and steel flow and things like that. So, so hydraulic models really is an essential tool to understand a utility system and understand what it's doing and its operational parameters. And what we've learned from doing this time after time is that if you develop it correctly from the outset, if you take the right approach to doing this hydraulic, or to building a good hydraulic model for your utility system, it can be the foundation of this continuous improvement approach that I mentioned at the beginning. So talk a little bit about how we do it and some of the lessons we've learned, or some of the tips we've learned from building these utility models. Marketing folks like me to break it up into 3 easy steps, but I think they're kind of 3 complicated steps. So the first step is measurement. You've got to have good information, good data. And in utilities case, utility systems aren't typically well instrumented, so that means going out in the field, looking at these systems, measuring, getting flow, pressure, temperature, whatever it is you need to get a good basis for that model that you're about to build in the second step. Which is that second step is model development. So in a utility system, the devil's kind of in the details. These are, again, giant spaghetti bowls of systems, and so you've got to get your arms all the way around your systems. A lot of times what we see is an engineer that's focused on some kind of process improvement draws as small of a box as possible around their modeling effort when it comes to utilities. And so what you end up with is a lot of simplification, and you don't really understand how that system operates because they tried to answer that question in their little box and make sure that everything was okay on their components, their system, or their part of the system, but they don't look at the system as a whole. And so that's really important to do. And then the third step is something we don't see often enough either, is maintaining it. So if you go through all this effort to build this big utility model that reflects that system, you've got a good current condition model that is behaving like it is in the field today. You've got to maintain that. So that accuracy is not permanent. That system is going to change over time. And so you've got to put effort into maintaining that model that you've built. So we break it into 2 phases. First is the bear hug phase. So this is where you're going to get your arms all the way around the system. This is going to spend a lot of time understanding its demands, its capabilities, its limitations. And once you've done that kind of big first effort, you're ready to start answering the real questions that probably got you looking at that system in the first place. So do your analysis, do your what ifs, look at your different scenarios to understand what's happening. The second phase is that evergreen phase. So this is the maintenance phase. This is where you're keeping your arms around the system, stay in front of your problems, prioritize, manage, and track issues, things like that, to effectively meet your demands and make sure that your utility system isn't the reason for some kind of problem with the process down the road. So I'll talk a little bit in detail about model development. Your model's got to be comprehensive and multi-purpose. So if you start with the approach of just drawing your box around your problem, then you're kind of going to miss the mark. So you've got to start from the outset to be able to answer any question with that model, and you may answer your specific question that got you modeling in the first place, but if you design it right from the get-go, then you can answer a lot of questions coming down the road. So you've got to aggregate all the key data in this model. So there's a lot of, again, these systems are so large that there's a lot of information that has to be put into it. So that's your design data, your physical data, your historical data, all that information needs to be reflected in that model in a current state. And if you've done your job right here, it ends up being better than PFDs, P&IDs, plot plans, data sheets, and pie data, because it takes all of that information and reflects it in a single source or a single instant. And so what you end up with is a really good tool to do a lot of different activities related to a modeling system. So a couple of pro tips when you are modeling a utility system, hydraulic modeling a utility system anyway. Be consistent. This one probably goes without saying, but you want to formalize your modeling standards and your data standards and your reference data. Your models should look and feel similar, across the same site. So if you've got cooling water system A and cooling water system B, it should be easy for your user of the model to jump from one system to the other without having to reorient themselves and spend 2 hours trying to figure out which way is up. If you've ever inherited somebody else's complicated spreadsheet, then you know that it's pretty easy to understand what I'm saying there, because cleaning up somebody else's mess is always difficult. Traceability is important. So your references, your data sources, that all needs to be traceable. You need to have a trail of breadcrumbs so that you can follow where different pieces of information came from. That means documenting your operating conditions, the model boundaries, your limitations. So the last thing you want is someone else to use your model and use it in a way that it was never intended. So you've got to have good documentation on that type of information as well. Also recommend maintaining a chain of custody. Utility engineers don't tend to sit in that seat for very long. They sit, a lot of places where they put the new chemical engineer that's working their way up the ladder. So they spend a year or two to cut their teeth on site and then go from there. And so that traceability, that chain of custody is important when it comes to that model. Strive to make the model the best starting point for a wide variety of tasks. Again, if you've developed that tool correctly from the first place, then there's a lot you can really do with it. And then the last recommendation is commit the time. So systems as large as these can be a time and labor intensive process. So some of the larger systems can take, we do this all day and we're pretty good at it, but can take upwards of 3 or 4 months to get from the time you start looking at that first P&ID until you've got good results that you trust and can start making good decisions on. So if you've got an engineer that you've asked to model a system, it's not realistic to have them do all of their normal daily tasks while developing a good model, or at least in a reasonable amount of time. Evergreening. Again, a lot of times you build a model to answer a specific question and then you put that model on the shelf. And so you've got to resist that urge to just move on and do the next thing. You've got to maintain that accuracy and the value of that model because it does degrade with time. Again, utility systems are moving targets, but they are slow moving targets. And so you've got to keep up with them. Utility systems, again, serve multiple processes. And so while you may have answered your one question that you needed to answer, there's going to be more questions because these utility systems are serving 6, 7, 8, 9, 20 different units that one may be in turnaround and not go in turnaround for 5 years, but there's certainly going to be a couple other units going to change their impact on utilities. Same thing, commit to evergreen your models and reference data, so standardize that. Integrate it into your engineering phases, your engineering processes, your engineering cycles. Make a decision on when a model needs to be touched and when it doesn't. And I would advise you, don't let those small details get lost in the noise. So again, there's so many different components that can be connected to a utility system. If you can formalize that when you update your model, even though it's one small turbine or one small exchanger that might get turned on or turned off, don't let those details get lost in the noise. And if you've kind of traced all that back, then you'll have a good history related to that model. More pro tips on the evergreening. Be consistent. Formalize your evergreening requirements, so not just the way you build the model, but the way you take care of it. Formalize routine refreshment. Even if nothing's happened in the last 2 years to this utility, somebody needs to take a look and make sure that nothing's changed. Consistently remeasure and recalibrate. So go get fresh field data. Pull fresh instrumentation. Require those interim changes to be included because again, they may be useful in retrospect. And then last one I see a lot of places struggle with is build the institutional knowledge. So that model and all the reference data around it and the traceability, the chain of custody, all those things I've talked about, really the main point of that is to fortify that institutional knowledge. So you need to have a central source that kind of containerizes all of that information so that when one utility engineer moves up and moves on, moves to a different company, all that knowledge isn't lost when the next person that sits in that seat has to deal with that utility system. So you need a system to manage and track that system's ownership, changes to the issues, projects that have affected it, And I'd recommend you make it a company resource. So make it in a way that, you might have one utility engineer take care of that container of information, but make it accessible so that if anybody needs to touch utilities, which everybody eventually does, they've got access to that. So I've got a couple energy savings examples just in some recent projects that I'll talk about. First one I'll talk about is boiler feed water pumps. So this client was having trouble getting some boiler feed water to one of their remote users. And so they asked us to come out and do it and develop a hydraulic model, and we did a lot of field testing related to that so that we could validate that model. So I think in this case, we logged pressure and flow for a week in 14 places throughout 14 pressure locations, flow in 8 locations, so we could get a good understanding of that system and its operational envelope and what it was doing. And what we found out, because we kind of went that extra mile to get that model good and valid and trusted, is they had a control valve that they had artificially raised the set point on for a nearby user so they could try to force water, to the remote user. And what that had done is it had backed all these pumps up off in their curves. So now their operating pressure was high. These pumps had pretty flat curves, and so they weren't getting the flow performance they need. And so because we had that good information, because we had a good model, we were able to demonstrate that, hey, lower that set point of that curve, and now you get a whole lot more flow, and you still got enough headroom from a pressure perspective to get it where it needs to go. And so what this allowed us to do was prove to them that they could shut off one of their 4 600 horsepower pumps. So this ended up, a no-cost change. They were able to save 10,000 kilowatt hours a day. So that wasn't a trivial one. Another one is raw water pump optimization. So this particular system had 5 pumps that fed 2 clarifiers, 2 systems that were jumpered together that were feeding 2 clarified water systems, or feeding 2 clarifiers. And so they were getting ready to put in a new cooling tower, so they wanted to make sure they weren't going to tax their raw water system too hard. And so we developed a hydraulic model. Same thing, we went and measured flow and pressure so we could get a good calibrated model that was reflective of what was going on that day, or at the time, the current conditions. And what we were able to do with that model as well, though, is to help them come up with a pump combination operating map. So we were able to map out, these are the best combination of pumps to operate for 4,000 gallons a minute, and these are the best pumps to operate for 2,000 gallons a minute. And so that you always have the most efficient pump combination operating depending on the different demands as they fluctuate throughout the seasons. This case, 1,600 kilowatt hours per day of savings on average, not quite as big as the boiler feed water pump, but again, this was no cost beyond that cost of the study, so it's a pretty good benefit for them. It also reduced some wear and tear on some control valves at their clarifier inlets, so they were throttling their pressure right at the end of the control valve. Last one I'll talk about is the cost of a spillback. So in this particular example, we're looking at, or we're working on a jockey pump system for their firewater system, and we noticed that they use a spillback to maintain pressure. And so this particular site was using one of their firewater pumps, and then they would use a spillback to just maintain that pressure. So they would just dump all this water that they had picked up out of the river, put under a bunch of pressure, and then they would burn it across that spillback valve and dump it in the river. And so we did a usage survey to understand where the water was going and what it was doing, and we were able to prove to them that 3,600 kilowatt hours a day is wasted by picking up that water and just throwing it back in the river. So that's not just the cost of running the pump, that's the cost of the energy that went into that water and then you just threw right back in the river. And so just that little exercise alone was enough to prove to them that, hey, consider a VFD, the payback period's pretty quick on this, so you can actually control that pump in a much better way. And in this example, there's also some water savings, so we're looking at recycling some wastewater effluent. So I think the site used about 1,500 gallons a minute, so that reduced their footprint by about 25%, or at least closed the cycle for about 25% of their water usage on site. Food for thought. If you're looking for energy savings in utilities, parallel pumps are there's almost always opportunities there. We stare at those systems all day, every day, especially if they're not clones of each other. So if you've got a bunch of mix and matched pumps, they like to push each other around, especially, and keep each other from being at their best efficiency point. So pumps don't always play well with each other. Another opportunity we see pretty often, cooling water is a good example, but consider the impacts of operating less pumps. So we do a lot of cooling water models, and we can get those pretty accurate. And one of the things we can prove to the client is, you might have 4 800 horsepower cooling water pumps circulating flow, and that fourth pump is only getting you an extra 10% of flow. And so maybe during the cooler months of the year, you've got the temperature and velocity overhead, or headroom, excuse me, to turn that pump off. You know, your exit temperatures will be okay, your flow velocities are fine in most cases, and so you might be okay. So 4, 5, 6 months of the year, you can shut off one of these gigantic cooling water circulation pumps. Control spillbacks in general, or wasted energy. You know, we see these all the time in refineries. It's kind of the nature of the beast. But if you've got a spillback, or if you're burning energy somewhere, typically that's some kind of opportunity to save some energy. So a VFD is kind of the obvious example. If you can control that pump, control your inlet pressure a little bit better, there's often some energy savings there. Piping, this one's a little more obvious. If you're cramming a bunch of fluid down, especially a long pipe run, and burning a lot of pressure, that's energy loss. And so sometimes there's opportunity to parallel pipelines or things like that in terms of energy. And then the last one is leaks. So we do a lot of leak surveys, insulation surveys, things like that. So if you're putting energy to squeeze steam or air or a fluid into a pipe and it leaves that pipe system before you've had a chance to use it, that's an efficiency of 0 for that volume that you've lost. And then don't forget insulation. While you may not be leaking a specific fluid, you are leaking heat, which is energy. So, kind of wrap this all up. You know, again, utilities do better with a continuous improvement approach. Require comprehensive hydraulic models be developed for all your major utility systems. These are giant systems, they're hard to manage. A hydraulic model ends up being a really useful tool to manage them. Require the modeling of any changes. Anytime you touch that system, even if it's taking a pump down for a couple months to swap it out or whatever, use that model to understand the impacts. And then require that you evergreen those models. You know, it's a significant investment to get a good utility model of some of these larger systems. And so it's a lot cheaper to maintain that model and stay up with it than to start over every 3 or 4 years when you've got the next turnaround coming. Step 2, leverage that model to make those incremental improvements. And you've got to accept small improvements. Again, there's tons of components that are tied to these utility systems. And so if you can make an improvement on component 1, 2, 3 of the 300, eventually you're going to get a net gain in efficiency. But you've got to accept small improvements. There is no utility project that's going to fix all the problems in a utility system. You've got to just make these small individual improvements. Well, one thing we recommend, and project managers don't love this one, but consider small improvements every time a project touches utility. So if you've got a process improvement, process expansion, make sure that they leave the utility system in a better place than they found it. You know, most projects want to make sure that utility is going to meet their needs, and they check that box and they move on. And so it's not unreasonable to make them improve the utility system incrementally anyway. Last, retain and fortify that knowledge earned. So build that institutional knowledge. It's important, or you're going to be fighting those same battles over and over. So that one's pretty obvious. But you can formalize that revision control, formalize your chain of custody, formalize that reference data, formalize how you track all the information and supporting data around that utility model. And then if you need to go all the way back to step 1 to revise your standards, that makes sense too. That's kind of part of the continuous improvement cycle in general. And of course, this is a service we offer to our clients. So this is one of our main things, is we build and maintain a library of utility models so that your utility engineers who are busy and don't have the time to spend 3 years modeling all of their utility systems, we can get those cranked out pretty quickly and then maintain them for you so that your utility engineers have the latest and greatest tools at their fingertips so they can quickly make decisions about their system. So we call it UMass. That's utility modeling as a service, but it's really the foundation and kind of the house, the container that helps you execute this approach. So that's all I've got. Again, my name is Clayton Harris. I'm the engineering manager for Hydrus Works. And I've got Corey Hensley. He's over there as well. He's my business development director. All right, easy enough.
Hi, thanks for your presentation. Do most of the clients, do they want to take over the model and change it themselves, or is it only that you offer it as a service to maintain it?
We typically offer it, allow them to take it over.
Okay.
Or maintain it for them, and that way, and we make them, we teach those engineers how to be dangerous with the model, because, you know, the last thing we want is them making a bad assumption
Yeah.
about the tool. So we kind of bolt on as their modeling group. And
Is
then-
it built in a commercially available tool, or is it a spreadsheet that you then provide to the owner? Or?
Yeah, it's commercially available, so
Okay.
AFT's Fathom and Arrow are our favorite tools. So,
Okay,
but
perfect.
we can use, you know, we use whichever one the client likes, but that's the best one. So.
Okay. And you include the control valve characteristics so that it can
Yes,
see that? Okay, excellent.
that's the devil that's in the detail. All of
Right.
those little details have to go in there for it to operate as it does in the field. So,
Okay, excellent, thank you.
thank you.
Thanks, Clayton. Appreciate it. Interesting talk. What's your experience about the economics of variable speed drives? Are you seeing that there's a good uptake on those, or is it difficult to justify them?
I'm sorry, the economics.
Economics of variable frequency drives. You talked about VFDs as part of your solution here.
Well, you know, we don't see a lot of VFDs in refineries, and so a lot of times it's kind of a new concept to them, or they'll say, "Yeah, we don't have room for that," and it's like, well, here's the economics. Most of the time, it pays for itself pretty quickly, but it's one of those things that energy is becoming more important, and I've been doing this for about 15 years, and no VFDs, go away, don't care, and so now it's becoming a lot more palatable for our clients, and so that Firewater example. I don't have the payback, but it was pretty quick from the grand scheme of things, because it was a relatively small project, but the VFD was it was just a line item cost. It was not a major cost, and they had the space for it in that case.
So with these very old systems, there's things have disappeared, instrumentation has kind of vanished. You're getting into something that's really, you don't know how, you can't even measure it. Have you found any kind of tools for non-intrusive measurements with some of these systems that are helpful when you go out and troubleshoot?
Sure, so it depends on the system. So water systems are you know, we can get nice and accurate with those because an ultrasonic flow meter can get you a long way. Steam might be the example that's much harder to measure without good online instrumentation. But we spend a lot of time in the field. We've got a lot of, well, I'll call them tricks to get a good measurement of the system. So as an example, we've got a lot of pressure loggers. So if a system's moving and changing a lot, we'll go pepper the system in pressure loggers, and they'll all go take snapshots of that. We'll sync them all up with time so that they're taking a pressure snapshot of that system. And when you combine that with a couple of flow meters, you can actually just kind of start backing out different flows in different places with that information. So we're pretty used to not getting good information and coming up with good ways to get it on your own. So does that answer your question, kind of? Air. So you can measure air with an ultrasonic flow meter. It's got to be the right conditions. We've done it before. We did one time where we had 7 flow meters all logging at the same time, and the task of the day was to go babysit those flow meters and make sure that they weren't airing out. And you know, ultrasonic meters in particular are not terribly precise, but when you have no instrumentation, it's much better than nothing. And so, yeah, we use a lot of flow meters, a lot of pressure logging, a lot of temperature measurements.
And now the mic holder gets to ask a question. Back in my day, when I started, I was a utility engineer who was on the job for 2 years doing steam balances. The biggest problem I would have would be with the turbines, the small turbines under variable loads. Any clues how you handle that these days? Do you tie into the process computers?
You know, so we try to use as much real data as we can. And again, steam's one of the tougher ones to measure, but you know, when you're building a hydraulic model, if you've got good flow data, then you've got a lot of trust in what's actually going on. But if you don't, then you're looking at data sheets and you're dealing with the problem that you're talking about. And so there's ways to back out actual, from horsepowers or RPMs, there's ways to back that out. And we do that all the time. It just depends on which piece of equipment you're looking at and how you can make a good estimation. And then also, is it on all the time? Is it off all the time? Or is it on for, rundowns or whatever it is? And so it depends is the answer. And I know that's not a great answer, but.
So it's the big lumpy stuff that you just deal with it.
Yes, yeah. And it's, like we just finished a steam system for a giant system, and it had 500 users across 3 systems, and we got as much information as we could, and there were some statistics involved because that's the best way to get a good feel for the system. So we just don't have information on everything. So.
Thank you.
Thank you.
All right. Our next speaker is Matthew Derner. He's the Manager of Business Development of Education and Training Resources at Hydraulic Institute Pump System Matters. And today, Matt will present on designing pump systems to reduce energy consumption towards greater sustainability. So please welcome Matt.
Okay, perfect. Thank you. I'm going to refer to some notes here. I gave this presentation in Portland, Oregon yesterday at a energy efficiency conference, and it was 7 hours long. So I'm going to try to condense it into about 30 minutes today. So I don't want to give the impression that we're going to leave here today understanding how to design a pump system, more so how to recognize opportunities for energy efficiency and optimization, and efficiency to us equals reliability. So hopefully that we'll walk away with that. A little bit on the context on the Hydraulic Institute. If you're not familiar with it, we're a trade association representing all manufacturers of pumps in North America. We're about 107 years old today. Generally best known for ANSI accredited standards organization. So you'll see Hydraulic Institute standards generally where you see pump systems at. Pump Systems Matter, which is the educational foundation of the Institute, is which I manage. So I manage the education and training as well as the energy efficiency for the Institute as well. A little bit on the Hydraulic Institute, just some key points. Driving all stakeholders towards a sustainable future, advancing solutions for pump system performance and efficiency, developing standards and technical resources, and educating the global marketplace, and being an advocate for the industry. Pump Systems Matter, driving all pump systems run at best efficiency point. I manage the board of directors for Pump Systems Matter, and that statement is in our mission cycle, or our mission statement. So, the goal is that every pump system runs at BEP. Is it realistic goal? Probably not, but it's certainly something we can work towards. Developing, delivering training and tools focused on increasing pump system efficiency and reliability. The Hydraulic Institute, again, represents the trade association that represents pump manufacturers, from all types of pumps, rotodynamic, positive displacement. So there's on that side of the fence, on the HI side of the fence, there's a sincere focus on pumps. On my side of the fence, it's more of a holistic approach of the system and how pumps play a part in valves and all the other ancillary components that play a part in the system. HI, just to back up, HI, we have members, which are the pump manufacturers, but we also have associate members that are the ancillary components of the system. So the VFDs, the motors, the couplings, bearings, AFT Fathom, any IoT that play a part in the system is part of our membership. As well as the EPC firms, the consulting firms that are standards partners that utilize our standards on a regular basis when designing systems. Some learning objectives we'll go over today: energy savings and life cycle cost of pumping systems, a pump curve review, system curve review, pump efficiency, pump system optimization, pump system assessment, DOE regulations, and the ER label, and then a list of HI free tools and training resources. Again, this is a lot of stuff. It's high level, but certainly all this information is readily available on our website. If you look here, the Department of Energy, on the left, we can see where the Department of Energy has looked at systems with motors, and what they determined that 25% of all pump or all systems that have a motor have a pump attached to it. So as you see here in the blue in the back, that indicates pump systems, and below it the next line, which is I believe the pink, that's compressed air, and then it comes down into to fan systems and other processing systems. On the bottom, you'll see different industries. So if you look at the back, the blue obviously outweigh the majority of all systems in regards to opportunities for energy efficiency. Life cycle cost of a typical pumping system. Pump systems generally, as you know, can last 10 to 20, 30 years or longer. Over this lifetime, the initial cost is minimal portion of the total LCC. Focusing on minimizing energy and maintenance will allow us to address the largest portion of the LCC, as you can see in the pie here. For existing systems, we focus on optimizing these systems. We can generally save anywhere from 20 to upwards of 65% or more. As energy costs continue to increase, pump manufacturers understand that making equipment more efficient will contribute to saving energy, while traditional methods of specifying and purchasing piping, valves, fittings, pumps, and drives often result in the lowest first cost. These methods often produce systems with unnecessary expensive energy consumption as well as maintenance costs. So just a brief overview of the pump curve and what we're looking at. Again, when we go back to pump systems matter, for one to fully understand how to optimize or assess a pumping system, one's got to understand the fundamentals of pumping. And that's generally one of our challenges in the industry when it comes to the Institute is the assumption that everybody understands affinity laws, or everybody understands what BEP or AOR or POR is. So that we've changed that assumption, and now we've gone back into more of a fundamental approach, especially with majority of the industries with tribal knowledge actually leaving, and new students joining the industry. So if we look at this pump curve, what you'll see on the curve itself, the BEP right in the middle, that's the best efficiency point. That's what we're targeting for. Energy savings are important, but in many cases, the non-energy benefits outweigh the energy benefits. In order to financially justify an improvement, often you need to include the total cost of ownership. So if you look, energy costs is at the top consideration, but there are also values for non-energy benefits from high reliability, increased productivity, less equipment wear and tear, reduced production losses, environmental impact, and increased plant safety. We'll go back to this in another slide, but if you'll look When you're left of BEP or right of BEP is when bad things can certainly happen. Best efficiency point, again, it's the rate of flow and head at which the pump efficiency is at its maximum operating point, where reliability is maximized. If you look at this example here, it's hard for me to see it from here, but it looks like the best efficiency point is at 85%. And if you'll look at the flow rate, so you're looking at 3,400 GPM, we'll be at about 85% at the best efficiency point for this indicated pump here. Single operating point, when the pump curve and system curve are overlaid, both as a function of flow rate, their intersection is the system operating flow and head. Note that they're really inverse of each other. That is, the flow is going up as the pump curve lowers while the system curve rises. You can note that on this curve here that the operating point is in fact to the right of BEP. Real world operation uncertainty. In the real world, there's a variation and uncertainty in both the pump curve and the system curve that result in operating range over time. You have to account for variation in system head, the age, the level of the system, and potential variation in the pump curve, and come up with a range of flows and head where the pump may operate. Simplified pump curve, understanding that it's not always possible due to uncertainty to get a pump to operate at BEP. So we aim typically for the POR. Generally the POR runs to either side of the BEP, preferred operating range for POR. So if you look at generally 70% of BEP on the low flow side, which is the left side of the curve, and about 120 above the BEP on the high flow side for centrifugal pumps. Here we're looking at a single curve with generic preferred operating region depicted for a centrifugal pump. Some systems are variable and require operating outside the POR. Therefore, we also have an allowable operating region, which is the AOR. The AOR is depicted here generically, but wider range of flows where operation may be acceptable. We try to stay out of this as much as we can here. The range of the AOR depends on the pump type and the certain system factors. Again, efficiency equals reliability. Depends on who we're instructing, whether it's an operator at a water treatment plant, or a design engineer, an application engineer, a reliability engineer. Each discipline looks at efficiency and reliability, and they generally have different definitions, if you will, for those terms. So we try to remember that efficiency generally equals reliability. They work hand in hand. Again, we're looking back at this the curve again, and this diagram impacts on pump reliability when the pump is operating outside of its allowable operating region. Note, most of the issues occur when the pump is operating to the left of the design. So if you look here, anywhere from discharge recirculation, which there's actually we've got suction recirculation, and then we've got a illustration of what suction recirculation looks like to the left of the curve. But the majority of the problems you're going to have are on the left side of the curve. Right side, we start moving into cavitation and really damaging the pump. So we'll go into system curve, and this is where I really, we spend a lot of time on system curves and how to change the system curve from a design perspective in new designs. It's hard to change the system curve in an existing system. So I didn't spend a lot of time here, but what I do want to show is kind of an overlay. So you've got the pump curve, as noted in the intro slides. The pump head and the system head will be the same. Similar to the pump system, or the pump, the system has a curve that is inversely sloped as a function of flow rate compared to the pump curve. See if I can get it to change here. Therefore, the pump curve and the system curve will intersect at its operating point. So if you'll see here, the pump curve on the left in the blue, indicated with the BEP in the green with its efficiency, and then the system curve, as you put those two together, you get the operating point, which, at this specific instance is at BEP. So that is where you're going to find the most efficiency when it comes to the curve. This is a system equation for developing system curve. I tried to keep this one as simple as I could, but I couldn't. If you'll look at the energy or the head required by a system can be described by physical equations. Shown here is the view from the pump. And remember, the pump will add energy required to the system. In order of the equation in the red box that you see there on the right, the pump head will be a function of the pressure difference. So it's H2 minus the H1 in the illustration. Elevation differences Z2 minus Z1, with velocity head differences V2 over 2G, and the friction loss with the system FL over D plus sigma K times V2 over 2G. In the red box, the equations are based on velocity, but if we have an existing system, we can usually simplify as we've done in the blue boxes, substituting flow rate Q with coefficient C and the velocity terms, because we assume the friction will remain proportional to velocity. The final blue equation simplifies the equation further by assuming the pressure at point 1 and 2 are equal. If the levels were equivalent, points 1 and 2 we could remove the Z terms, and system would be totally friction head. So that's as simple as I can get with the system curve. Pump efficiency. Definition for pump efficiency is ratio of pump output power and pump input power expressed as a percentage. What is a pump and how does it consume power? Pump is essentially something that moves liquids, as you can see here. And I'm gonna answer the question on the VFT that was asked a minute ago. There's a place for VFDs and there's not a place for VFDs. The assumption in the industry is that, and I say the industry, I say from a pumping perspective, that if you put a VFD on it, it becomes more efficient. That's not necessarily the case. In some cases, that is the case. But I've seen a lot of times where you put a VFD on a constant flow application and it turns nothing more into a very expensive soft starter hanging on a wall. So maybe that answers the question. So there's good and bad. There's certainly we certainly don't want to give the impression when we're optimizing our assessing pump systems that just put a VFD on it, it's going to become more efficient, because that's not necessarily the case. If you look here, we've got, if you're familiar with the term wire to water, where we are calculating the overall power consumption from into the extended motor product, which the extended motor product being, in this case, the VFD, and then you've got the motor input into the driver out of the VFD, and then from there into the pump input power and out. We've got to consider all those efficiencies going from the left to the right. As you can see, indicated from the arrows on the left, you obviously have more power going in. I lose efficiency as I go through a VFD and then through my driver, which is my pump, and then obviously through the pump itself. So that's my wire to water efficiency from in to out of the entire pump system. This is generally the same indication here. It's going to show the efficiency going in from the backside of the motor. I can determine pump efficiency, motor efficiency, drive efficiency, and again, overall efficiency, just simply by performing these calculations. Now we'll go into pump system optimization. What is pump system optimization? It's the process of identifying, understanding, and cost-effectively eliminating unnecessary losses while reducing energy consumption and improving reliability in pumping systems, while meeting process requirements, minimizing the cost of ownership over the economic life of the pumping system. Ultimately, minimizing the cost of ownership over the economic life of the pumping system. Opportunities in new design and existing design. Generally, if you look at new, if it's a new design, we certainly have better opportunity to design the system because we can look at the whole system holistically and make sure that we look at each component and design it with the best components in mind. Sometimes on existing systems, you've got to take the system you have and then try to embed it with some efficient components. Effective cost reduction of pumps. By choosing different pumps, the pump curve can be adjusted. The pump efficiency and BEP also adjust. The pump curve can also be changed by changing the impeller size or fixed speed. So again, if you adjust your impeller or if you add a VFD or a control method, you have a potential of actually changing your pump curve to become more efficient or closer to BEP. Affecting cost reduction system. The system curve can be adjusted by using different pipe sizes, different layout, different pipe material, different components. Generally, your friction coefficient is really your opportunity for reduction in the system itself. The pump curve can be adjusted using variable speed control, as I indicated before. The system curve can be adjusted to a limited degree by decreasing pressure drop across high pressure drop components. And again, there's some opportunities for existing systems, repair the pump, impeller size change, VFD, potentially a new pump, and then in new systems, the opportunities reside in changing anything. The operating point itself can be changed. Cost reduction opportunity is much larger. Additional factors, impeller trimming. For this example, the efficiency at BEP decreases from 86% at maximum diameter to 82% at the minimum diameter of 9 inches, I believe it is. Again, if you're interested in that standard, we've got the ANSI HI 14.3, which it references the standards in regards to impeller trimmings. Pump system assessment. I have one slide on this. We developed, and I'll probably jump to this one here. We developed the only pump-centric certification or accreditation in North America. It's PSAP, PSAP, which stands for Pump System Assessment Professional. This was developed in conjunction with the Department of Energy and some utilities like PG&E in Southern California. They came to us and said, with the DOE making regulations on pumps, we're running out of opportunities for incentives for our ratepayers. Lighting's been done. We've done all the LED lighting. We've compressed air. We're working on all that. With the knowledge that pumps are a large consumer of electricity, there's certainly an opportunity to decrease their load. So when these utilities started coming to us and wanting to build these incentive programs, there's custom incentives for pumps that can be found daily. We're seeing more and more utilities that are developing deemed incentive plans around pump systems. The problem was who had the requisite knowledge to actually go in and perform an audit of a pump system. They didn't have anybody. It wasn't the lighting guys. The lighting guys weren't going to stop doing lighting and jump into pump systems. So what we did was we actually developed the PSAP about 3 years ago, or 4 years ago. So those who hold this credential basically say, I have the knowledge and capabilities of performing a pump system assessment. DOE regulations, HI energy rating. How am I on time? Am I good? Okay, great. As with everything else, Department of Energy kind of steps in, and again, they realize that there is a large opportunity for energy savings and taking a burden off of their grid. So back in 2020, actually 2016, they came out with a NOPR and the regulation for the Clean Water Act. So this is it's the law. Those 5 pumps that you see there, in suction frame mount, in suction close coupled, inline, the OH3, OH4, and OH5, radial split, multi-stage vertical inline diffuser, and the vertical turbine submersible. All of those that are manufactured for clean water applications, not that they're in clean water applications. Those pumps that are manufactured for clean water applications are regulated now by the federal government. The reason they regulated was they determined that 25% of the pumps that were being manufactured in the industry were not efficient. So they established, I don't know if you're familiar with the PEI, the Pump Energy Index. They established the PEI and determined 1 as the baseline for the PEI. So anything less than a 1 could not be manufactured or sold into the United States. So you'll see a PEI CL, which is the constant load, and then you'll see a PEI value for any variable load that fall into these pumps here. I can tell you we are currently working on the regulation for circulator pumps now. We suspect that by the end of the summer that circulator pumps will be regulated. We're just about complete with the regulation. And I suspect after that, we'll start adding additional pumps into this, these 5 pumps that are covered here. These pumps, just to give a better context, believe anything over 200 horsepower. I want to make sure I don't give you the wrong information here. So generally pumps that fall between 1 to 200 horsepower, greater than 25 gallons per minute, and less than 459 foot of head, and 1,800 and 3,600 RPM. Any of those pumps fall into this category. They are regulated by the federal government. So what we did was we took the manufacturers, again, that we represent. They wanted to make sure that they provided some validity or extra level of validity in the products that they manufacture. So they came to us and with a approved lab. So we audited a third-party lab for each manufacturer. Some of them that it's actually their lab. We had to go in and audit it, and they perform additional testing for their pumps. So we've got a database. They upload all of their pumps in our database. Those pumps are now being used as a qualified product list for utilities such as PG&E, Southern Cal Electric, Encore. There's 25 utilities across the country that are using our database as a qualified product list for pump incentives. What we did was we went past the PEI and developed a ER rating, which is the HI energy rating. So essentially, we took the ER, divided it by 100, or I'm sorry, we took the ER, which the baseline is 1.0, minus the rated PEI. That's the number that's actually on the pump that the federal government stamps, and then multiplied it by 100. So what you'll see here is essentially that this is what an ER label looks like. It may be a little difficult to see. This one here has a PEI of 0.40. Again, the baseline is 1, so it certainly falls within the baseline. Anything above 1 would be would not be able sold in the U.S. or manufactured in the U.S. So this one has a PEI of 0.40 with an energy rating, our ER label of 6.0 or 60. The higher the number, the more efficient that pump is. So in our database, you can pull these energy ratings. The energy rating, this one is just a pump, a bare pump. You can actually, I can add a extended product to this ER label and come up with a new value. So if I added a VFD, I knew what the value of the VFD was, or a new motor, and sold this as a system, I can give you an extended product ER label with that value on there. The intention was not to use it as a selection tool, if you will. Is it? It most probably certainly is. But I mean, it's given the industry indications on the most efficient pumps out there. Wrapping it up, HI and PSM free tools and training resources. On our website, you can find many tools from flow modeling tools that we certainly use in our optimization and assessment. Measure, which is the DOE's tool for PSAT. We've got a pump savings calculator on there. If any of you've got the old Hydraulic Institute blue hard copy book that was made in 1963-ish, the Engineer Data Library is essentially that book with all these are free downloads. So I would I'd suggest going on to pumps.org and taking a look at some of this stuff. Industry knowledge path. We just completed a pump fundamentals or pump industry fundamentals body of knowledge, which outlines knowledge areas that individuals in certain disciplines and in certain industries, it's the knowledge they should have to work in the pump industry. Whether I'm an application engineer, I'm a design engineer, I'm an operator, you can go through this body of knowledge and it will identify the level of knowledge for each principle that we identified. It can be used for workforce development. It's actually being used now for certification. So we're going to have a certification by the end of the year, which is a pump industry certification. So a level 1 certification, if you will. So if someone was coming in the industry and they're sitting with a hiring manager and they provide them with a CV and a level 1 certificate, you have a really good idea of what their knowledge is in the industry. And then we've got the core courses, which are the pump system fundamentals, pump system optimization, pump system assessment. We take a lot of these courses, and I work with, on the energy efficiency side, I work with the DOE in supporting the industrial assessment centers across the country. So, these IACs that are going out and actually performing audits in their geographic territory, some are not familiar with pump systems. Some are more familiar with compressed air. It's easier. It's find the leak, lighting. It really depends on the staff of the IAC and what their knowledge area is. So we're supporting the DOE and the IAC by providing them courses to further knowledge in the pumping industry. So I believe that is it. I probably went over, but I apologize. That's all I've got. Thank you. So I'll be glad to answer any questions as long as they're not highly technical. No, I'll try my best. We've got some really, our staff, if you've never heard of the name of Peter Gaden, he's our Deputy Executive Director, Technical Affairs Director. He's by far the smartest pump guy I've ever met. So I'll share his information and any major technical questions in regards to standards, or he can certainly answer them. But if there's anything I covered today, I can try to answer for you.
Thank you for the presentation.
You're welcome.
One application I have experienced in my career is about produced water from oil production, right? After you separate the oil, the produced water is usually re-injected in a deeper underground formation. So the pumping is very intense, of course, high volumes, high heads. Have you experienced applications like that, and what advice would you give in those kind of industries in terms of pump efficiency and everything?
Yes, we've experienced it, but it's, being a trade association, we get a lot of it secondhand from our manufacturers. So, they provide us with case studies and hopes that we'll, support the industry and with education on that. So for that specific topic, in all honesty, with reuse, I'm going to refer to Peter Gaden on that one. So I apologize.
So Matt, thanks for the presentation. Good overview. In your talk, most of it was referenced to water. Do you do much work outside of that area? I mean, obviously a lot of people here are involved in refineries, chemical plants, things, pumping hydrocarbons and so on.
Yeah, so yes is the answer. We work closely with API. I mean, a lot of our ANSI, our standards reference API 610, B73.1, and again, we're represented from we split pumps down the middle from rotodynamic or centrifugal to positive displacement. The industry's been heavy on the rotodynamic side. I mean, we've got a lot of manufacturers that are members and have been members for a number of years. We're getting more and more members on the positive displacement side, so we're starting to get more applications in the positive displacement in oil and gas. I can tell you that I've got a number of oil and gas individuals that actually sit on two of our committees right now from here in Houston. That one is on an intake design, and the other is on our cavitation committee. So so various industries. It's not exclusive to water. Water's what's being regulated now. So from an energy efficiency standpoint, again, if you buy any one of those 5 pumps and you put it in an application outside of clean water, you're still regulated by the federal government. It's how they're manufactured. So.
So I guess my question would be on the placarding and labeling of the efficiency on your pumps. You'd mentioned that anything with a number of less than 1 is not allowed to come in. I guess that's a follow-up on the API standards. If the pump is not necessarily for a clean water application, it may be sized or gauged for something that's not necessarily clean water. Efficiency is not within that below 1 range for that application. Is that reflected in the label? Is that allowed to come through for another application, or how's that handled?
I'm trying to, when it becomes DOE, I really try to, I'm cautious in how I answer. A lot of the regulations, whether it's appliances, the DOE, if you look at their regulations, they regulate it off of shape and size of something. they're not sure what the functionality is. They don't know where it's going. So, you know, unofficially, can I put that in an application that has absolutely nothing to do with clean water? Yeah, it happens every day. Is the efficiency going to change? No, the efficiency is going to remain the same. I mean, those are tested based off of the standards for efficiency testing. So regardless, I mean, I'm not going to pump, you know, a product, a highly viscous product through a water pump anyway. So generally, I'm going to get something that's close to specific gravity of water. So the viscosity alone is going to change my, you know, the efficiency. The test was with clean water. Yeah.
Import, if it's not allowed to be imported, if you said that there's a limitation on non-domestic pumps.
If it's sold into the United States.
Yes, yeah. And then something like a positive displacement pump for something more viscous that maybe for that particular application, so the efficiency still has to be above that or below the threshold of 1.
Below the threshold. Right.
Gotcha. Okay.
Yeah. I don't foresee, it's probably on their list of things, you know, to look at down the road, DOE. I mean, they've got a lot of other things they've got to do, but positive displacement pumps are probably not on the priority list. There's just too many and too many different applications. So it's, but the Hydraulic Institute is well represented by PD manufacturers.
Like two-phase, I mean, gun fluid. Do you have anything on that? Or you, what type of system or what type of requirements are there from code point of view?
Yeah, I mean, through our optimization course.
Yeah, repeat the question, please.
Yeah. Okay. The question, I believe, if you don't mind repeating the question, I want to make sure I got the question right. It's for
Critical fluids.
Okay.
Okay, well, many times CO2 at high pressure, ethylene, and other fluids are pumped across the country in pipelines, and they are being used as pump starter compressors. So I just want to know if you have anything on that.
So that's more covered in API standards than it is in HI standards. I've seen it more in API than HI, so I really don't. I can't provide any more context to that. API covers that.
Well, in the interest of time, I think let's thank Matt once again.
Thank you.
And let's welcome our next speaker, Mr. Jack Heiberger. He is the Managing Director at Attenborough Water Americas. And Jack will today talk about energy in transition, reverse osmosis, and economics of green hydrogen production. Over to you.
Thank you very much. Thank you for having me. Yeah, so I'm going to keep it pretty high level as well. Get kind of an overview of the economics of green hydrogen production and kind of the energy transition conversation that we're starting to see. It's interesting that this event is happening kind of at the tail end of OTC as well. I traditionally come from the upstream side of things, and so I'm going to give kind of an overview here. That's a big picture of myself, so I'm going to skip right past that. The abstract that was kind of on the front of the presentation there is how reverse osmosis, hot and bore water, has been in the water industry for many years, and reverse osmosis desalination is our kind of area of expertise. But then how does that fit into all the conversation that we're seeing now around the energy transition, kind of the next generation of fuels and energy sources? And green hydrogen is one of the things that the industry has seemed to kind of rally around, and then all of the the byproducts of that, maybe ammonia for alternative propulsion. And so I'm going to talk a little bit about how electrolysis and pure water reverse osmosis fits into that. Hot and bore as itself, and the reason this is going to be, I'm going to be the first one to use the highlighter. The reason I highlight this is just because hot and bore water has been around for a long time in the Netherlands. I have a colleague here of mine from the Netherlands since 1906, and the only way that happens is by being adaptable and adapting to the industry. They started with water taxis, bringing water out to vessels in the port of Rotterdam, and then from there, it's like we should also produce the fresh water on board. We should provide the analysis, the equipment that provides that fresh water, and that's going to become relevant as we move into this a little bit. Around the world, a lot of installations we respond to the offshore industry. Probably 75–80% of our business is all offshore and support vessels, maritime applications. But some of those locations are also near the downstream refining complexes, and that's relevant here because energy and water have always been very tightly connected. And in this day and age, as we'll get into, you've probably seen in the news, water becomes increasingly scarce. And how does that fit into the energy sector, downstream, upstream? That balance becomes ever more fragile. And so how do we fit into that? Historically, evaporation has been one of the main solutions to provide fresh water. There's a couple of different technologies there. Historically, one of the first MED plants, multiple effect distillation plants to do desalination was installed in the Netherlands Antilles back in 1928, I think. And so that was historically the way a lot of this desalination and freshwater production took place. But you know, the energy efficiency considerations and the improved quality of filtration systems in the membranes and reverse osmosis systems has started to make that become the preferred solution. And that then moves into just strictly reverse osmosis. I think people are a little bit familiar in here, but that's a basic process using a membrane to filter fresh water out of salt water. There's a natural osmosis. I don't know if anybody remembers back in biology class trying to put your textbook under your pillow and studying for an exam by osmosis, thinking it's going to go in that direction. But fresh water naturally wants to go through a permeable membrane to reach an equilibrium with salt water on the other side of that membrane. Reverse osmosis is simply the reverse of that process, as if you were going to download from your brain back into the textbook. What you do is apply a mechanical pressure on the other side to overcome that osmotic pressure and then force the fresh water back in the other direction across that membrane. That membrane then filters the water to reach the level of purity required. A lot of what we do at Hot and Bore is for drinking water applications. So big offshore vessels will use reverse osmosis plants to produce fresh water on board for drinking water. So I realize that I'm talking to a technical audience. So normally what we would say is what is removed? Everything. Never speak in absolutes. Everything as far as drinking water is concerned. You do see that at a certain level, metal ions and some things are not going to be removed unless you use a second stage, which I'll talk about here in a little bit. But you know, from the size of a human hair down to a couple of microns, that's what we're talking about filtering through reverse osmosis. So I'm touching on the downstream side of things. I'm again, like I said, more upstream, but I think you guys are all familiar with reverse osmosis, or at least water purification for downstream purposes. Steam cracking, boiler water, I think we talked about earlier, pump applications, cooling water. All of those processes in downstream refineries require fresh water. And here I have it, again, potable water also for facility applications, but cooling system, boiler feed water, steam cracking, delayed coking, even you would use some water for cleaning those tanks. And so those are some of the requirements of refining water. And so I bring all of this up because For reverse osmosis, and from our point of view, we're familiar with some of these applications and the level of purity, the water purity required for these applications. And so that's going to transition because we kind of have that experience and that history in these applications. In the energy transition is, how are we going to take some of these processes and some of these applications that we all have, many years of experience with, going back, in hot and bore's case, 100 years, but with refineries and downstream applications, how do we move and take that same knowledge base and that same experience into the next generation? And I pointed out that, we're right here at the end of OTC, and if you walk around the OTC, you see a lot of companies that are no longer oil companies or drilling companies or petrochemical companies. They're now energy companies. And the reason they're talking about that is because they have the experience, they have the engineers, they have the knowledge, they have the installation base in many cases, they have the offshore assets even, that can then be used in this same transition. So I think it's not so much a zero-sum game. Some people think like, oh, as long as we're talking about renewables or transitioning into the next generation, we're somehow taking people's jobs, or taking money that we've invested in infrastructure from one sector and moving it to another, where really I think it's all about adaptability and just like I mentioned with hot and bore, moving through 100 years, multiple generations, and adapting to new developments. So some of the traditional barriers, when I've been in various sectors of the industry, and I still to this day I see friends and old colleagues of mine on LinkedIn or wherever taking kind of pot shots at this energy transition, and what are some of the typical barriers you see to this? One is the economics of it, which I'll talk about. Infrastructure. In many cases, many companies have invested a lot in offshore infrastructure, and what does that all become obsolete at this point, and we have to do all new things. Politics and government really come into it as well when you talk about government subsidies and how are we going to finance the scaling and some of the investment required to move into an energy transition, and the technology goes along with that as well. Oh, I didn't realize this part was animated. So this kind of speaks to some of our history in the offshore industry. We traditionally provide reverse osmosis and this technology to offshore platforms. And we really advocate a complete solution to provide safe water on board, not just for the technical applications, but also for drinking water and all of the hotel and accommodation services on offshore platforms. And there is a long history. We've been in the industry for a long time, and we've provided water systems and reverse osmosis to offshore platforms. And again, with the transition, does that then mean that we can't transition once we move away from some of the traditional offshore platforms that we've provided desalination systems to? No, it's really that we're really providing the same knowledge base and expertise, just to a different end. It's a different means. It's the same means, but to a different end. And so we can provide this reverse osmosis system to platforms regardless what they're producing. So here, we have the knowledge base, we have the knowledge, we have the technology to move into this next generation, this next energy transition. And I kind of joke sometimes with my colleagues, my Dutch colleagues, that where a lot of times maybe Europe has a plan for 2030. America's is maybe 2050, but as soon as you say, as soon as you point out and you start seeing the economics of it, and we can make money at it, the U.S. is pretty well adapted to making money at these things. So we have the technology, we have the knowledge base, the people right here in this room, we can make this transition. And so a little bit of background on hydrogen itself. The main three, there's kind of a big color palette. It seems like it's ever expanding. The main colors we're talking about are gray, blue, and green. And if you're not familiar, this may be a little simplistic, but just to give context for everyone, gray hydrogen production is when you're using steam methane reformation. You need water for that application, but that's using hydrocarbons to produce hydrogen, but it has carbon dioxide as a secondary production, and so you're still polluting in the sense of renewables and green and carbon sequestration. So that's the gray traditional. We're making hydrogen, but we're still emitting greenhouse gases and carbon dioxide. Blue, you're basically doing the same thing. You're just capturing it and sequestering it or reusing that carbon dioxide for another purpose. Green is when you're really becoming green. Now, instead of creating that hydrogen using hydrocarbons or releasing carbon dioxide, now you're using renewable energy sources, and there are no secondary emissions. There are others. Brown is coal gasification, which on the spectrum, I guess, would be even dirtier than gray. Turquoise uses pyrolysis. Pink is basically green, but using nuclear instead. And I feel like everyone's trying to get in on the game. We just got to come up with a color. Gray, blue, and green are really the ones we're talking about here. And so we have experience. We're producing, yes, I got a chuckle. I was wondering how my Big Lebowski reference was going to go over. But we have the experience. Steam methane reformation, creating blue and green, or gray and blue hydrogen. We know how to do it already. We have the technology, we have the experience. If you want hydrogen, I'll make hydrogen. That's what the Gulf Coast, I think, is saying. That's what we know how to do. We have made hubs, for LNG ports and distribution and all these things. We'll do the same thing. It's just now for hydrogen. So gray and blue, I kind of went through the colors, but both processes require a large amount of fresh water, and that comes into the economics of things. Where are you going to locate these plants? How are you going to produce this gray and blue hydrogen or the green? Basically, through green, you're going to be using electrolysis, which is converting basically the H2O into H2 and O. But then steam methane reformation does the same thing to create, but you need water either way. So that's where hot and bore comes in. These are the basic reactions for the existing gray and blue production of hydrogen. You're taking methane and water, you're splitting them with steam, with pure water is required, but then you're producing, in SMR's case, carbon monoxide, which is a bad word, but also hydrogen. But then there's the second stage. The water gas shift reaction is on the bottom. You're then taking the carbon monoxide that you formed, again using water, to now produce CO2 and H2. So hydrogen is the end goal there. Ultimately, you're producing some carbon dioxide. Either you emit that or sequester it, and that's the gray and blue piece of it. So as I mentioned, on some of the barriers to making this transition are economics. It's the cost of electricity to switch from the traditional gray and blue over to the green. It's the infrastructure costs, and frankly, water input costs are one piece of that puzzle as well, and then just general supply chain issues that we've seen in the last couple of years. But the economics are there. You see some of those charts, that's some of the cost per kilogram of hydrogen on the top right. It is more expensive than gray and blue, but the projections are going to bring it down. How do we make that transition? How do we make that the more economical solution so that we're producing maybe the next generation or the next fuel of the future, alternative fuel, but also not harming the environment and creating the emissions that we're doing with gray and blue. The market demand there on the bottom for hydrogen, a lot of it is for refining purposes, ammonia production, and a small piece of that is the transportation. You've probably seen in the news a little bit, hydrogen fuel cells, which are currently used maybe for small, forklift type applications, but I think Toyota is now creating a hydrogen vehicle where the only emissions would then be water. So that the demand for hydrogen is increasing. So how are we going to meet that demand? And how are we going to do it with the assets here? Green ammonia has been, especially in the maritime industry, where most of our experience comes from, using ammonia as an alternative fuel. Today, most of that demand from the chart on the previous slide for ammonia goes towards fertilizer, but ammonia is also being looked at as an alternative fuel. Engines are already being designed to utilize hydrogen, but also what I'll get into on the offshore side, and where some of the conversations I've had with Alan before and where this topic came up, is once you produce that hydrogen, how do you then get it to market? How are you going to send it through pipelines and avoid some of the hydrogen embrittlement problems that would happen there, or use ammonia perhaps as a carrier? And so that's where a lot of the hydrogen future is going. And then this gets into just kind of the economics of it. In economics class in the past, I had a professor that always talked about public goods being non-rivalrous and non-exclusionary, and street lamps were always the example. It's hard to get sometimes people to invest in something when, an example of a street lamp, you can't prevent, if your street needs light and you put a street lamp in, you can't prevent everyone from also taking advantage of that benefit. It's also not consumed. One person can't take up all the light in any way. So how do you finance projects that are really a public good? And this kind of topic came up talking with a colleague on the hydrogen production side, because with hot and bore water, we do freshwater production on board vessels. We also put that into bottle filling stations, for example, to eliminate single-use plastics while these vessels are at sea. And in clean beaches, not having the Great Pacific Garbage Patch, with all the microplastics floating out there. Who's going to take care of that? Who's going to invest in the things that are required to protect those public goods? And the electrolyzers and the scale that are required as a part of the economics of producing green hydrogen to avoid some of the secondary knock-on negative externalities of the traditional oil and gas and hydrocarbon market for gray and blue hydrogen production. How are we going to scale up the electrolyzers and the wind farms, renewable sources that are required to do that? And here's just kind of a simplistic chart on where that investment comes from. And this gets into sort of the politics of it, where some people think it's kind of a zero-sum game because there are subsidies to invest and to kind of catalyze the scale of the technology required to produce green hydrogen. Existing technology, not very risky, not a ton of capital required. Small business, you can put that on your credit card sometimes. If it's becoming increasingly risky or a lot more capital required to invest, that's when you would start getting, private equity, VCs to start investing in it. But if it's super high risk, super risky technology, super new, at that point, the only way you're going to get that moving forward is with a little subsidy from the government to kind of push and support those public goods that are really in all of our interests. It's just, the small time capital is not going to be able to take care of that. So green hydrogen, I've talked about already where that's going to come from. It's going to come from electrolysis. It's going to come from fresh water. And how do we scale that up and produce green hydrogen? Electrolyzer technologies, alkaline is kind of one of the existing ones. Proton exchange membrane, PEM, means a little bit, that's a newer technology, is a little more expensive, but a little quicker ramp up time. But these are the things that need to be invested in so that we can make this transition. But in order to electrolyze water to produce hydrogen, there are pure water requirements. And this is the kind of adaptive piece that I was talking about earlier. We're familiar with pure water requirements, even for hydrocarbons, even for downstream traditional refinery applications, even for steam methane reformation, for gray and blue hydrogen. We're familiar with these requirements. We can go back and look at the reverse osmosis. We remove everything, not quite everything, everything for drinking water purposes. Looking at some of the electrolyzer requirements today, they require either ASTM type 1 or 2 water. ASTM 2, we could reach probably with 2-stage reverse osmosis, where reverse osmosis takes the seawater, produces what we call permeate and condensate. Permeate is the produced freshwater, condensate is the now concentrated salt water that we discharge. And then you would then produce that, run that fresh water again through a second stage reverse osmosis to get it even purer. Type 1, that is even really beyond reverse osmosis technology. That will require some EDI technology, electro-deionization, which we can also do with partner companies. But this is the level of water that we're trying to achieve, and it's only through electrolysis and pure water production that we're going to achieve these levels. So water and green hydrogen production, as I said, you need fresh water to produce it. You could you could electrolyze, that is, seawater, but with NaCl, with salt in there, you're going to have the risk of some chlorine gas production. And also, we do electrolyze seawater today, but not to produce hydrogen. at the bottom there, from a stoichiometric perspective, it's about a 9-to-1 ratio of water to produced hydrogen, but efficiencies in the system, without going into the details, is going to require a lot more than that. So where are you going to get that water from? That's where the economics come into it. And there is no more abundant source, really, than the Gulf of Mexico or the seawater right next door to the places that are trying to produce this water. So I went and I actually found, it's funny that I think Matt mentioned a study from 1963. This is actually a Department of Energy study looking at freshwater consumption by the refining industry, and their survey took place. It was a 1963 report, but they surveyed the refineries back in 1955. But 3.5 billion gallons of water was withdrawn daily for use by petroleum refineries. By 2014, U.S. energy required 58 trillion gallons of water, and 3.5 trillion of that was fresh water, or 10% of all U.S. Consumption. And this is a graph that they used in that 1963 study. But you see then 86% of the water used that would ultimately go towards the refineries. A bulk of that, 91%, I think at the time, was used for cooling, but the rest of the water was used for boiler feed and the other refining processes. But 86% of that came from surface water. Today, that's a little riskier. On the right, you would see where am I going? If I'm going to install and subsidize or invest in a hydrogen production plant, where might I want to do that? A green hydrogen production plant. Well, I'm going to look at a place where I can have the renewable resources required. So if you look on the right, wind speeds and solar radiance, overlay those two maps where you get the best wind and the best sun. That's also the same on the left as the places with the highest water scarcity and the highest risk of drought. So land-based green hydrogen production is going to be a bit of a problem, because where are you going to get the water to electrolyze, even if you have the renewable resources to provide the electricity? Probably heard in the news a couple of news items recently. Avocado farmers in California use a lot of water. They're trying to see how can we avoid paying for city municipal water to use for our crops. Also in the news lately, how are these states going to agree on how are we going to use the dwindling resources of the Colorado River? The Mississippi River was recently, in a drought condition, receding. They're finding shipwrecks and dead bodies. I will say, from a reverse osmosis perspective, if you have shipwrecks and dead bodies, you're going to need some additional pre-filtration and treatment before you get to your membranes. Membranes have very high filtration, so they block easily, and dead bodies tend to do that. Groundwater, though, even if you're going to use groundwater, freshwater, rainwater, there is still impurities that need to be filtered. You're not going to get to the ASTM 1 or 2 level water just by using groundwater. Looking at time, I'm going to start going a little faster. I see you looking at your time as well. Thanks for keeping me honest. Looking at the Gulf economics, this is a study from the Bureau of Ocean Energy Management, NREL, as well, looking at where the economics in the Gulf are really coming from. The green area is the highest return area. That's where the strongest winds in the Gulf are located. But you partner that with the existing infrastructure, the existing knowledge base in the room, the existing knowledge base from producing fresh water for refineries. Offshore production is really going to be where the economics make sense, because we can take the seawater, we can treat it, make it into fresh water. The wind resource is there, and we're not taking water from land-based scarce resources. So if you want to go invest in some property in Port Mansfield, that might be a good spot for a hydrogen terminal. But short of that, we have the infrastructure, we have the knowledge base, we have the platforms, idle platforms in many cases, we have the pipelines out there ready to switch into this green hydrogen production scenario. It's just we need the investment and the push. So reverse osmosis from a water specific perspective and from Hottenbor's point of view, water is a key ingredient into moving into this next generation and some of these alternative fuel sources that we're looking at nowadays. And yeah, this is just some examples of some of our water makers. But I'll wrap it up there. Thank you very much for your time and attention. If there's any questions, thank you.
Thank you for the nice overview. A question regarding reverse osmosis. I believe this is a very energy-intensive process. And what are the opportunities that you see to further improve the energy efficiency of reverse osmosis? So when we produce hydrogen, we can have an overall positive effect.
Yeah, I think in the context of the energy requirements, say, of a platform that we might be looking at for hydrogen production, the reverse osmosis, the energy requirements of pumps and things for reverse is really minuscule and compared with the larger requirements of the system of electrolysis and systems like that. The alternative would be, evaporation or things that already consume more energy even than reverse osmosis. So in the scale and the grand scheme of things, if you make a little, say a little hydrogen producing topside that you remove from a platform and put this new hydrogen one, the water purification, the reverse osmosis can be a small piece of that. So, yeah.
Very good presentation, thank you.
Yeah.
What pressure the electrolyzers are running?
What pressure?
Yeah. What pressure hydrogen comes out of the electrolyzer?
Oh, that's a little, I'm not sure, to be honest. Not on the electrolyzer side, we would provide the water for the electrolysis. That would be probably a question for the electrolyzer manufacturer, but I'm not sure.
Because hydrogen is difficult to compress, that's what I'm saying. That's the reason.
Yeah.
Yeah. And what is maybe somebody need to think about what to do with the oxygen coming out.
Yeah, I mean, breathe it. I don't, no, I mean, but yeah, there could be a secondary, but one of the economic questions that does come up with hydrogen production is what is the offtake? Who you find you produced hydrogen, who are your off-takers for this? Unless there is the, hydrogen fuel cells or or maybe ammonia, for fertilizer, but where are you going to get this offtake? And really this investigation that we've been looking at offshore hydrogen production would then involve the economics of it. How do you make the return on investment, quicker, frankly? And one piece of that is, as water does get, scarce on land, maybe you're also you could produce more water than is required for the electrolysis, for example. Maybe water is an offtake, but yeah, maybe oxygen is an offtake as well. I'm not sure, yeah. Yeah. Okay. Mm-hmm. Okay. Yeah. No, and that's everyone remembers the Hindenburg. I mean, there are dangers with hydrogen. The ammonia, hydrogen embrittlement in the pipelines. How are you going to take care of those secondary effects? There are people looking into that already, with lining the pipelines, for example, with ions or other materials that would then protect the existing steel pipes from hydrogen embrittlement. So yeah, it's all concern. There's not, it's not a blank slate, a pure angel of you got to consider a couple of secondary effects. But I think the net gain for the environment and for secondary carbon dioxide production, all of that kind of thing, is going to be net positive for hydrogen. Yeah.
Hi, could you talk a little bit about the maintenance and reliability of RO, like for your offshore rigs, et cetera?
Yeah, so for our ROs, there is some flushing of the membrane that takes place. We have a clean in place system where you're flushing you do have to take it offline for a little while, but you're flushing the membranes. Other than that, there's not a ton. There's some operational, filters and things that are required, but Yeah, I'm trying, that would be, we can, some more details, my technical colleague from the Netherlands could probably answer, but yeah, there's some maintenance requirements, but they're fairly minimal. Fouling is one concern, of course, depending on the source water coming in and what the membranes are actually filtering, they could block up quickly. You would have to then flush them more often. But yeah, that'd be one of the main concerns from a reverse osmosis perspective. Yeah.
Jack, so I haven't heard much about offshore hydrogen production yet. You might be the first person presenting on that, but it's obviously a big source of water. Curious, I mean, a lot of water would be required, much more than 2,000 cubic meters per day. What do you think, or maybe the brine management of from reverse osmosis? Like, how would that be done in a responsible way?
Yeah. Yes, I mean, the brine, so yeah, there is, say, 40% of freshwater production out of seawater, and then you have the condensate on the other side, brine management. I think in most cases, I mean, depending on where something is located, you can't always just dump that right back in the ocean. I mean, it's a small drop of the bucket saltwater-wise back in the ocean. But in certain requirements or certain areas, that is a concern. You could, for electrolysis, it would require a little bit purer water, so you could run that through again to make it pure. But yeah, then you're going to have to. That's a good question. Yeah, depending on where you're operating, there are, state versus or federal versus open water. Yeah, there's going to be some questions there. Yeah.
Thank you. One question that I had was, so we know that like green hydrogen comes from renewable sources, but is there typically a renewable source that's more commonly used than others, or is it typically just dependent on what's more like accessible and abundant in an area?
Yeah, that's a good question. I mean, it's really an economic model, really. Working with other pieces of that puzzle, where are we going to get these various things? So, as I was showing on the map, yeah, there's some great places on land, for wind and solar, for example, but then that's not a great spot to take your fresh water from, or water sources from. On the map towards the end there, looking at the Gulf Coast, over towards Corpus Christi in the Gulf, at least, that's where the stronger winds are. So that's going to be a better location for if you're going to use wind turbines. But part of the calculation there, honestly, is how far are you to the next terminal, or if you're going to be sending electricity back to shore instead of hydrogen, then if you're far enough offshore that you're going to have to start with DC and then convert it to AC to send it back to shore. So there's kind of almost a heat map you would have to generate to calculate what the best combination is. And the other pieces of the wind is not always blowing. So maybe you partner that with solar as well, and maybe make a central hub from various sources, and then the hydrogen plant here, and then send it back to shore. Yeah, even hydro power, taking wave power from the swells. Yeah, it would just be a calculation. But I would say wind, I think, would probably the first one that people talk about generally, and then solar. But yeah, it would probably be some optimal combination of the two, depending on where you're going to locate your plant. Yeah.
Got it. Thank you.
Thank you. Yeah, I'm wondering, one region in the world that you occasionally hear about is the Middle East, where they have a lot of need for water, and also some of the Middle Eastern countries have a lot of water. And so they're able to and willing to pay a lot of money to get water, whereas here with our economics, we still hope to find water on the ground as often as possible. But are there really any trends or developing technologies that seem to be centered in the Middle East, or being, I guess, tried out in the Middle East?
Yeah, that's that region of the world is not my particular area of expertise. I mean, yeah, there are coastal desalination plants that even we have installed, in Africa and other locations. Other strategies for producing fresh water in those regions, I'm not sure. would suggest reverse osmosis, but no, yeah, I can't give you any more detail on that. Maybe if you after the session here, if you want to ask my colleague, he may know from Europe. He probably has a better perspective on that.
Any more questions? Alan, I'm all the way over here now, so. Okay, nothing.
I was keeping an eye on time because I know I'm the last guy preventing you from getting dinner and drinks. So I was trying to stay on time, but if there's any other questions, let me know. Yeah. All right. Thank you.
All right, this brings us to the end of the technical program. Please give a big round of applause to all our 3 speakers and our sponsors who made this event happen. And yeah, please also join us in our future events from TIEEP and also our sister organization, TEEN, which is Texas Industrial Energy Efficiency Network. And if you have any questions, want to learn more about these organizations, we are joined also by Alan Rossiter, who is the Executive Director for the TIEEP. And the next event from TIEEP will be the TIEEP Fall Energy Forum. The details are not yet finalized, but they will be announced on the website. Feel free to navigate through this website or through the QR code to learn more about these. Couple of more announcements. If you have not pre-registered today, please find at the desk the register. Please share your email address and names, and we will be happy to invite you for our future events. We are also looking for continuous improvements for our for TIEEP and other event organizations. So we'll be happy to receive any feedback, any comments or suggestions that you have. This is the QR code for providing us with your feedback. And as we mentioned in the start, this is the QR code for the PDH certificates. So this finally brings to the end of the water forum. But before we disperse, I have an announcement regarding the facilities tour from San Jacinto CPET. So Jay will be organizing the tour along with his colleagues, and it's about 20-25 minute tour. And I have taken that tour before, and I would highly recommend it. But one thing of caution that you cannot take any beverages there. So please first take the tour, and then meanwhile the bar will be open after that. Okay, and there are options. Okay, and so we will have a STS-AICHE dinner meeting after this, and if you have not registered, there are a few spots open, and if you want to register and stay for the dinner meeting as well, we welcome you to do so. For those who are online, please note that there will be a different link for the STS-AICHE Teams meeting, and we will see you at 7 p.m. for that meeting. With that, let's thanks once again all our speakers and attendees, and Jay will be happy to take you on the tour.